Welcome to Ask and Learn.
Here we have a half-life problem, and the model we use for half-life is m of t equals m naught e to the kt. This is the exact same model that we use for population growth. We're just using an m instead of a p, and we can expect the value of k to be negative instead of positive since it's going to be decay and not growth. So let's use the given information and do part A to find basically a general equation for the mass at time t. So we know the initial mass is 100 milligrams, and we know the half-life is 30 years. So if we want to substitute 30 for t, we can put half the original amount, which would be 50 milligrams, in for m. So we have 50 equals 100 times e to the 30k, and we'll use that to solve for k. So we'll divide both sides by 100, and we get 0.5 equals e to the 30k. And then we'll take the natural log of both sides. So natural log of 0.5 equals 30k. And then we'll divide both sides by 30. So k is the natural log of 0.5 over 30. So we put that into our model, and we get m of t equals 100 times e to the natural log of 0.5 over 30 times t. Now that would be fine to leave as our model, but there's also a way to simplify the expression that we have, the power of e. So let's take a look at how we might do that. So if you have e to the natural log of 0.5 over 30 times t, that could be rewritten as e to the natural log of 0.5 raised to the power t over 30, because if you multiply the exponents, it's the same as power to a power. Now e to the natural log of 0.5 simplifies to be just 0.5. So we have 0.5 to the t over 30. And if you want to think of 0.5 as 1/2, and if you want to think of 1/2 as 2 to the negative first, we have 2 to the negative t over 30. So if we want to, if we have a reason to, we can substitute the expression that we had in the model for 2 to the negative t over 30. So that gives us m of t equals 100 times 2 to the negative t over 30. That's an alternative form of our model. Okay, now let's move on to part B. And in part B, what we want to do is find the mass when the time is 100. I think it's 100 years. So we just take one of our two models, it doesn't matter which one, we substitute 100 in for the time, and we put it in the calculator and approximate it, and we get about 9.92 milligrams. And then for part C, what we want to do is find the time when we have 1 milligram. So find t for the mass equals 1. So we can substitute 1 in for mass into either one of our two models and solve that for t. So we're going to divide both sides of the equation by 100, and we get 0.01 equals 2 raised to the power negative t over 30. And we're going to make some more space here. So that was 0.01 equals 2 raised to the power of negative t over 30. We're going to take the natural log of both sides. And then we can use the power property of logarithms to bring that power down to the front. So now we have the natural log of 0.01 equals negative t over 30 times natural log 2. Now what we want to do to get t by itself is we want to multiply both sides by 30 and divide both sides by negative natural log t. So that gives us t equals 30 natural log of 0.01 divided by negative natural log 2. And then we put that in the calculator, and we get an approximate value of 199.3 years. That's the time it would take for this substance to decay to 1 milligram.